Sharp law from UCL, also talking about imposing boundary condition with blood flow simulation and MLB. So Sharp.
Thank you for the introduction. So I'm going to present you a recent study on imposing boundary conditions on the outlets of a large arterial network. In addition to myself, this work is contributed by John and Peter. So the creation of the virtual human is one of the goals in ConBioMed. This requires the development in to capture the human biology at all scales. And today I'm going to bring us closer to achieving simulation of blood flow at the full human scale. Since in the audience, you may be already familiar with HemLB, so I will skip the introduction of this. So what I'm going to talk about is how we impose the boundary conditions. Due to some constraints in the resources, sometimes the simulation domain is truncated and you just focus on the domain of interest. But this requires some accurate representation of truncated systems, as shown in the gray area in the left figure. And this the strategy to impose boundary conditions must be efficient and scalable, being able to scale up to a large arterial network. So common strategies include imposing the pressure or the traction at the boundaries. More sophisticated strategies include imposing the flow rate plus some assumptions on the flow profile. And a rather accurate method is to couple the main solver with reduced order models. But this requires some parameters tuning in order to have an accurate representation of the truncated system. So the right figure shows an example of such a coupling system in which at the three outlets, there's a circuit or a reduced order model attached to it. And there are some parameters that you should tune it. So Greenberg and Kaniadakis proposed an efficient strategy to impose the flow rate ratios at the outlets. The relation in this strategy is that the flow rate is inversely proportional to the resistance in the reduced order model. So because it requires only one parameter, this can be scaled up to a large arterial network. So they show that this model is accurate if the resistances in this model are sufficiently high, as shown in the results in the right figure. So here our contributions is to clarify the general role of the model parameters in this strategy, namely the resistance and the capacitance in this reduced order model. We study the impacts of these parameters on the stability, accuracy, convergence of the simulations by varying the model parameters using like a parametric analysis. So to give you a better understanding of this strategy, I'll first go to the rather basic concept of this. So in fact, the blood vessels can be conceived as an electric circuit. The pressure can be is analogous to the voltage, flow rate versus electric current, flow resistance versus resistance, wall elasticity versus the capacitance, flow inertia versus inductance. So imagine the whole human circulatory system can be conceived as just a large electric circuit. That's amazing. So this Greenberg strategy relies on the rather simple or relies on the two-element Windkessel model, which is simply a RC circuit. So the dynamics of this RC circuit is given in the formula on the left. And this model basically converts the flow velocity, which is given by the main solver, to the pressure, which is required by this solver. This model has the advantage of being able to filter high-frequency noise, which often hinders the simulation unstable. So I'm going to present how we approach this problem instead of just going to the results, because I think it's very crucial. And but however, in the next few minutes, it may be a bit intensive. So in this Greenberg strategy, there's a knowledge gap in which we don't know how large the resistance should be. They just say that, or we just know that the resistance should be high enough, but how large should it be? So first, for an arbitrary vessel, we can conceive it as a cylinder of a length L and radius R, such that the flow resistance is the same. Then the flow resistance is given by the product L times K, where K is given by the Poisson flow. So in the case of outlets, the total resistance, the vessel is attached to the two-element Windkessel model. So the total resistance of this system is given by the sum Lk plus R. So in Greenberg's relation, there's no dependence on this product Lk. So this suggests that a necessary condition for Greenberg's strategy to hold must be that the resistance dominates the product Lk. So as I mentioned, we don't know how large the resistance should be. So we use a parametric approach, and we introduce the parameter gamma R, which is like the scaling factor of this Lk. And we will vary this parameter in a range. Okay, similarly, for the other bundle parameter, capacitance, we do some analysis. Back to the dynamics of the two-element Windkessel model, the RC model, we find the homogeneous or transient solution. And the characteristic decay time is given by the product RC. In the bottom plot is the time series of the pressure. We see that there's some transient solution, which is some noise, and it is very it's unphysical, and we want to avoid this. So in order to avoid this, the characteristic time for it to decay is given by RC. So this RC shouldn't be too large. So we have this upper limit for the capacitance, where omega 0 here is the fundamental frequency. You can find it by like the period of the inlet profile. So for the lower limit of this capacitance, we find it from the Fourier transform of the partial differential equation. And we find that the pressure and the flow rate is actually has a phase difference given by the arctangent of omega RC. And this can be translated to a time lag in the time series of pressure and velocity, as shown in the left figure. Yeah, you see the peak of these two profiles has indeed some time lag in the experiments. So this gives the lower limit for the capacitance. And all in all, the upper limit and the lower limit suggest a parameterization for the capacitance, which is this formula. You can see another scaling factor, gamma RC, is introduced here, and the resistance is put on the right-hand side because it's given by the previous parameterization. Okay, this is the last slide about the strategy we use, which is about the desired flow rate ratios. So based on the principle of minimum work, we show that the flow rate is proportional to the equivalent radius of a vessel. With the mass conservation, this relation can be written as this form. So the significance of this relation is that we only need the information about the geometry, but not some data on the flow. This is particularly useful when the physiological data is unavailable. However, some studies show that this relation is not accurate in some conditions. For a more accurate description for a particular case, other powers other than 3 can be used. Okay, so I've already finished the most intensive part, and I'll now show some results in this study. First of all is the simulation domain. We use 2 domains, namely the 5 outlets domain and the profunda femoris. And the latter of which is a model for it's an artery in the right thigh of a human. Is the name of that artery. So we look at the stability of the simulations. Here I plot the parameters RC against R, and the green spots represent the simulations in which it's stable, and the cross means unstable. So we find that the stability increases with the value of the capacitance, which is given by the boundary of the 2 regions, the blue line here. And we also observe that the stability increases slightly when the grid resolution increases. This is expected because it can resolve more features in the flow. Regarding the accuracy of this model, we plot the simulated flow rate ratios against the desired flow rate ratios. So as the resistance increases, namely the color becomes deeper, we find that the plot approach the dotted line. Just the dotted line, which is the expected one, and the error decreases exponentially as this resistance increases. At the largest resistance tested, the error is within 7%. However, we also we observe some intrinsic errors, namely that the error doesn't approach 0 as the resistance increases. This may be explained by the fact that the simulation is not completely convergent. And this is about the impact of the capacitance on the accuracy. So we find that there's only a slight dependency of the capacitance in this aspect. This is also expected from the relation of Greenberg's relation, because in the relation there is no dependency on the capacitance. Okay, the next one is about the convergence and the fluctuations of the simulation. Here shows the time series of the flow rate against the flow rate at different outlets. So as the capacitance increases from the left to the right, we can see there are more fluctuations and the convergence rate decreases. So this is expected because the capacitance is related to the storage property, which can reduce the instability, and also is related to the phase of the flow. Okay, so in addition to what I said, the time lag is also observed when the capacitance is increased. So Greenberg's strategy is an attractive approach in which we can use it to for a large arterial system. And here we use a parametric analysis to understand what particularly the values of the parameters should be. We find that the value of the resistance should be larger than the threshold value. And we propose an estimation of this threshold value, which I didn't go into detail, but it's tested and shown in here. Another aspect is about the capacitance. I show that the capacitance doesn't have a strong dependency on the accuracy of this strategy, but it has impacts on the convergence rate and the fluctuation of the flow variables. Also, the simulation stability is also impacted by this parameter. As the capacitance increases, the stability increases. So our understanding here can provide a guideline for choosing these two parameters in practice. And the methods used here can be applicable to larger and more complex vascular domains encountered at full human scale. This study wouldn't have been completed without the support from these parties. So this is the end of my presentation. Thank you for listening.